All right, a little bit more applied for this one. In this video, I'm going to describe how to calculate the area that's between two curves. And this has already been mentioned as a type of motivation for doing antiderivatives and for doing integrals, that every time we were calculating an integral from a to b of some function, what we were really finding was the area, or usually the area, not always, that's between the function and the x-axis. We're going to expand on that here. I want to again motivate that this is actually what is happening. There's a quasi-proof in a different video that goes through the construction of the definition of the derivative and then integrates both sides to really show that there is a connection between antiderivatives and areas. But here I want to explore the idea using an experiment, or rather 3 experiments. So the first experiment is I want to calculate the integral from 0 to 4 of x dx, and I'll interpret it after we calculate it. Antiderivative of x is 1/2 x squared. Using the anti-power rule, we're evaluating from 0 to 4. So we get 16 over 2 minus 0. We get 8 as our answer. Now I'm going to draw a picture of that. We have our x-axis, we have our y-axis. We're going from 0 to 4 of a function y equals x. So y is equal to x. We're stopping at 4. If y is equal to x, then if x is 4, y is 4. We're looking for this area, because the claim is that the integral is the area under that curve. So area is 1/2 base times height, area of a triangle. The area, so 1/2 times the base times the height, 1/2, 4 times 4, which is also 8. So it worked out. I'm going to do the one on the far right. This is not y equals x, this is y is equal to 2. I'm just going to do the math first, and then worry about the geometry later. Antiderivative of 2 is 2x. Evaluating this from 0 to 4. So we have 2 times 4 minus 2 times 0, which is 8 minus 0, which is also 8. Now that's just, it's not meant, like it's not important that it's the same. I don't want to mislead you. It's not important that they're both 8. I'm going to draw a picture though. What is y equals 2? What does that mean? What is the graph of that function? So y equals 2 is a horizontal line, constant y value of 2. Now we're going from 0 to 4. So I'll put 4 down again. Oh. Draw a dashed line here. Not dashed, like shaded in the region, and then that's a rectangle. Well, yeah, area is length times width. Now the length is 4, the width is 2, so we get 8. It matches. Now I'll do the one in the middle. Antiderivative of 2x is x squared. We're going to evaluate this from 0 to 4. We get 16 minus 0, which is 16. Okay, I'm going to draw a picture of that. And this time we're not going to be able to validate the area geometrically. So y equals, oh wait, yes we will. What am I saying? Y equals 2x, so it's steeper. I'm going to have to draw a little bit differently. Yeah, we can validate this one geometrically. Of course we can. It's a triangle again, just a different triangle. Now my axis is going to be a little bit different. So I'm going to put 4 here, and it's 2 times 4, so there's 4. The y value will be 8 there. Okay, so there's y is equal to 2x. Now I'll draw the line down. Now we're looking for this area. I know the pictures, it doesn't look like it, but it's because my x-axis is scrunched. So I can make the graph fit. This area is 1/2 base times height. So 1/2, the base here is 4 and the height is 8. So I get 16. What's important is that each of these area calculations matches the integral. Not whether which one's bigger or smaller or the same. But we're just matching this 8 to that 8. We're matching this 16 to that 16. And we're matching this 8 to that 8. Now these are special examples of antiderivatives that we can match up with areas geometrically. We're in general not able to do that. We would have to trust that the integral is indeed giving us this area under the curve. So you'd have to go back to one of the earlier videos to validate this claim a little bit better, a little bit in a almost proof kind of way. Almost a proof that the integral from a to b of f of x dx is the area underneath f of x from x equals a to x is equal to b. Now I did mention that it's not always the area. We have to be careful about how it's constructed, how it's interpreted. The expression that will always give us the area is the following expression. The integral from a to b of the absolute value of f of x minus g of x will always give us the area bounded by f of x and g of x from x equals a to x is equal to b. The absolute values, what it does is it makes sure that all the heights that we're measuring in our area calculation are positive, because we want our area to be a positive quantity. We don't want negative areas to come out. So if the function ever dips below the y-axis, for example, this absolute value function would take care of that. It would compensate for it. It would force the area to still be positive. But if it's the case that one of these functions is always above the other function, so for example, say f of x is always larger than or equal to g of x, at least for x values between a and b, then what we can do is we can drop the absolute value function. So we can say that the area is the integral from a to b of f of x minus g of x. To map this back to the previous questions we were working on, what is this g of x that just appeared? Well, inside this picture, g of x would be the line y equals 0, just the x-axis. And the same thing in these pictures, g of x would just be 0. So subtracting 0 would not change what we're integrating. But in more complicated examples, like examples that would look like this picture, we do have a bottom function that's not the axis. And to construct the appropriate area expression, we do need that subtraction to be there. So a takeaway is that if we construct things correctly, if we are constructing an area expression accurately, we're going from the right left point to the right end point of a top function minus a bottom function, which is another way to represent this, the formula on the right hand side. And the top function is always above the bottom function, they don't cross in between. Then what will come out will be the area between the curves, and it has to be a positive quantity. If we do an area calculation, or what we think is an area calculation, and a negative result comes out, it's guaranteed to be wrong. So just watch for that. It means that we either constructed the expression incorrectly, or we have an error in our integral. You're going to find that these questions are hard to do, and they require a type of recipe to do properly. They're formulaic in most ways, so that's the good news. The bad news is the formula looks like this. It's a recipe, it's a process. The first step of the process is to know what your ingredients are, to be able to identify what the top, quote unquote, top function is and what the bottom function is. That's really easy to do if you're given a graph, and harder to do if you're not given a graph, because it means you have to make a graph. Once you know your top and bottom functions, you also have to know where are you integrating from. What is your left side of the integral? What is your right side of the integral? Sometimes it's just given, and sometimes it's not. Sometimes you have to find it. You would find it, if it's not given, by finding out where do the curves cross, where do they intersect. Once you have this information, once you have the top function, the bottom function, and the bounds of integration, you put it all together. Your area is going to be the integral from a to b of your top function minus your bottom function. And then you use various methods of integration, whether it's substitution, anti-power rule, or something else, to integrate and evaluate. So here's a straightforward example. The picture's given. The bounds are given. You're asked to find the area between the curves. So based on the picture, the top is equal to the cosine of x. The bottom is equal to the sine of x. Your bounds, you're going from x equals 0 to x is equal to pi over 4. So we can put it all together. We have all the ingredients. We can put them together into our area calculation. Area is the integral from a to b of top minus bottom, integrated with respect to x. So we have the integral from 0 to pi over 4, the larger x value, the smaller x value to the larger x value. And then our top function is cosine of x. Our bottom function is sine of x, integrated with respect to x. Now, it just so happens that these functions cross at pi over 4. Cos of pi over 4 is 1 over root 2. Sine of pi over 4 is also 1 over root 2. Okay, so we're going to take the antiderivative. The antiderivative of positive cos is positive sine of x. The antiderivative of sine of x is negative cosine of x. This is evaluated from 0 to pi over 4. Okay, so we have sine of x plus cosine of x from 0 to pi over 4. We can plug in the top bound. So sine pi over 4 plus cos pi over 4. That's the top bound minus the bottom bound. Sine of 0 plus cos of 0. So 1 over root 2 plus 1 over root 2. Sine of 0 is 0. Cos of 0 is 1. Now we have 1 over root 2 and another 1 over root 2. That's going to be 2 of them. 2 over root 2 minus 1. Now you might be worried. Is this negative? So if you're worried about that, how do you check? Well, you make a common denominator. So this would be 2 minus root 2 all over root 2. And now you can tell it's positive. Root 2 is around 1.4. What number multiplied by itself gives you 2? It has to be smaller than 2, right? So you have 2 minus something smaller than 2, so something positive, divided by root 2. It's going to be a positive number. Just as a check. But you would leave it as 2 over root 2 minus 1. Don't make common denominators or do weird stuff. I mentioned that sometimes the endpoints aren't given to you. You have to find them. Worse, so one of the worst things that can happen in a question like this is when the endpoints are given, or maybe only one endpoint is given, and either way, the functions cross at some point. And you have to find that out. You have to look for that. That's always a risk. If you're looking for the area between two curves, the functions cross. So why is it a risk? Well, let's go back to our ingredients. We need to be able to identify which function is on top and which function is on the bottom. If the functions cross, then which one we would define to be on top, which one we define to be on the bottom, is going to change at some point. And that's something we have to keep track of. So we'll start with a nicer type of difficulty here. The difficulty is, yes, the functions cross, but which one's on top and which one's on the bottom does not change if we want to find the area that's bounded by them. So find the area bounded by these two curves, y equals 6 minus x squared and y is equal to 3 minus 2x. And actually, I didn't screw something up, but I'm going to hide some information on the graph because this is another format of the problem. if this information, if what's given to you, maybe it has a picture, but maybe that picture doesn't have the axes labeled. Maybe the tick marks aren't there either. So you'd be left guessing. Where do these things cross? You can tell that one of the values is positive and one of them is negative, but beyond that, you'd be guessing, and don't guess. So here's the ingredients. We can tell what the top function is. The function with the highest y value for the area that we're going to shade in, the area that's bounded by the curves, the area that's contained by them. Bounded by just means the functions form a wall around the area. You can tell that the top function is 6 minus x squared. The bottom function is 3 minus 2x. But the bounds we have to find. And here's how we find them. If two functions cross, it means their y values are equal. So I'm going to set y equal to y. It means their x values are equal too, but it isn't helpful to say x is equal to x. But it is helpful to say y is equal to y, because then that allows us to say 6 minus x squared is equal to 3 minus 2x. I'm going to collect everything over on the right hand side. I'm going to add x squared to both sides. And then I'm going to subtract 6 from both sides. That gives me a quadratic on the right being equal to 0. Now a common factor, not common factor, I'm going to factor the quadratic using the product and sum method. What times what? So the mystery numbers, I need them to multiply to give me -3 and add to give -2. So I'm going to get -2 and plus 1. Or -3 and plus 1, my apologies. -3 plus 1, multiply to give -3, add to give -2. And then that's going to give me two solutions. X is 3 and x is -1. So we're going from x equals -1 to x is equal to 3. We're going from the lower bound to the higher bound. Okay, so we can put all the ingredients together and say that our area is equal to the integral from -1 to 3 of the top function minus the bottom function. So the top function is 6 minus 2x, or 6 minus x squared, my apologies, 6 minus x squared, and the bottom function 3 minus 2x. Okay. That's the expression. And that might be the whole question as well. The whole question might be what expression represents the area. And you would stop there, you would not continue, you wouldn't simplify it, you just leave it alone. But I'll keep going because it might be a whole calculation as well. So I'm going to simplify 6 minus 3, negative x squared plus 2x, plus because we have a double negative, and negative times negative is positive. And then I'm going to integrate each of these pieces. Antiderivative of 3 is 3x. Antiderivative of x squared is 1/3 x cubed. Antiderivative of 2x is x squared. And we're going to evaluate this from -1 to 3. And this is going to get a little bit ugly. We have 3 times 3, 9. And then we have minus 27 over 3, so minus 9. And then plus 9. And then the lower bound, we have -3. And then plus 1/3. And then plus 1. And then simplify. So 9 minus -2 plus 1/3. So 11 minus 1/3. So 33 over 3 minus 1 over 3, 32 over 3. I'll just circle that. Email me if there's any mistakes in these. It's easy to make little errors. That's why I like the ending the calculation of the expression. Here's another type. Made substantially easier if there's a picture. We're asked to find the area that's bounded by y equals negative x, y equals x is negative 5, and x is 4. If we didn't have the picture, we'd have to make it. At least I would have to make it. I can't do these without pictures. Maybe you can. I can. I'm going to graph y equals negative x. So y equals negative x is a line with a slope of negative 1 and an intercept of 0. I'm going to graph y equals positive x. Y equals positive x is a line with a slope of 1 and also an intercept of 0. And we can see that they cross at 0. So I'm going to write that down. They cross at x equals 0. Then I'm going to draw the other two pieces. We have x is negative 5, so that's this region here. That's that line I mean. Create this region. Oh. And we have the line x is 4. And we can tell whether the picture is given to us or we make the picture ourselves that there are two regions here. We have a big area and a small area. We're going to have to split our integral up into two. So area is equal to area 1 plus area 2. So for area 1, we're integrating from the lower number, negative 5, to 0 of top minus bottom, plus for area 2, we're going from 0 to the higher number, so 0 to 4 of top minus bottom. And the role of which function is on top, which function is on the bottom changes in each of these two areas. So for the first area, going from negative 5 to 0, and the top function, I'm just going to make a template here and fill in the template. Okay, so let's look at the first area on the left-hand side. We have a function on top, which is blue, and the blue one is negative x. And we have a function on the bottom that's red, which is just x. But those roles switch when we go to area 2. Area 2, the top curve is x, and the bottom curve is negative x. Just have to be careful making these expressions accurately. All right, so I'm going to simplify now. We have integral from minus 5 to 0 of negative 2x. And for the second region, integral from 0 to 4 of positive 2x. First region, antiderivative of negative 2x is negative x squared, evaluated from negative 5 to 0. In the second region, we have positive x squared, evaluated from 0 to 4, and then we can evaluate each. So negative 0 squared minus negative 5 squared plus 4 squared minus 0 squared. Okay, so we have 0, and then we have negative, negative, so positive of negative 5 squared, so positive of 25, positive of 16 minus 0, and we end up with the final answer of 41, which I invite you to calculate a different way. I invite you to use geometry The area of a triangle is 1/2 base times height, and you have two triangles there. You should get the same thing at the end. Okay, here's another one. Write down the expression representing, that's a typo, representing the area bounded by sine of x, 2x, from x equals negative pi over 2 to x is positive pi over 2. So this isn't the whole question. This is just to write down the area expression. So area is equal to integral from a to b of the top minus the bottom. But from the picture, y is equal to sine of x and y is equal to 2x cross or intersect at x equals 0. That means we have to split our area expression into two area expressions, a left part and a right part, area 1 and area 2. So I'll label those pieces inside. I'll put area 1, area 2. So area 1, we're going from negative pi over 2 to 0. And what's the top curve there? Minus whatever the bottom curve there is. Plus area 2, we're going from 0 to pi over 2 of the top minus the bottom, the x. Now let's look at the picture. In the first region, the higher y value, the part that's on top, is sine of x. But in the second picture, that's the bottom part. And the top part in the second region is 2x, and the bottom part in the first region is 2x. That's it. And I'll just color code those zeros. The zeros came from an analysis of where do the functions cross. That's where we switched we split the integral up. Here's another one. This asks for the whole calculation. We want to find the area of the region that's bounded by e to the x, 1, and x equals ln 3. So I'm going to pick on the bounds first. Well, we can get the ingredients. Might as well write this one a little more carefully. The top here is e to the x. The bottom is 1. Y equals 1. But the bounds are a problem. Only have one bound. We need two bounds. So we have to either use the picture or use some algebra. I'm going to use some algebra and show that it matches with the picture. We're going to check for where these functions cross. Where do y is equal to e to the x and y equals 1 intersect? So we're going to set y equals y. E to the x is equal to 1. Take the ln of both sides. Ln of e to the x is equal to ln of 1. Cancellation law, x is equal to 0. So that means our second bound is x is equal to 0. We're going from 0 to ln 3. And the picture tells us that. But I like to also pretend that we don't have a picture. So area is the integral from the lower bound, 0, to the upper bound, ln 3. Of the top function minus the bottom function. So the top function is e to the x, the bottom function is 1. And now we can integrate. Antiderivative of e to the x is just e to the x. Antiderivative of 1 is just x, evaluated from 0 to ln 3. So I plug in the top bound, e to the ln 3 minus ln 3. Plug in the bottom bound, e to the 0 minus 0. And then simplify. E ln 3 cancels using cancellation law. We get 3 minus ln 3 minus 1. So our final answer is 2 minus the ln of 3. And perhaps this is a worry. Maybe you would worry about this. Which is bigger, 2 or ln 3? So how do you compare? This is just an aside. You don't have to do this. 2 versus ln 3. So what if let's see. An exponential function is monotonic. It's always increasing. If I can show that e to the a is larger than e to the b, then that would guarantee that a is larger than b. So e squared versus e to the ln 3. E squared versus 3. Which is larger? Well, e is 2.7. What's 2.7 multiplied by 2.7? It's larger than 2 multiplied by 2. 2 multiplied by 2 is 4. So e squared is larger than 4. So I'm comparing 4 to 3. 4 is definitely larger than 3. Something larger than 4 is thus definitely larger than 3. So 2 is larger than ln 3. You can do that without a calculator. I'll erase that because the text on its own doesn't make sense. It needs the explanation. I don't want people looking at the note, not looking at the video, to panic. You don't have to do this, but I mentioned one way to check if you did everything completely wrong is to check whether your result's positive if you're looking for an area, and that's how you would do that without a calculator. Okay, last example for the next topic. We're going to find the area that's bounded by these curves y equals root x, x is equal to 1, and y is equal to 4. And the picture is not labeled, and I'm going to unlabel the axes as well. I'm going to pretend there's no numbers showing there. I don't want to give you the wrong impression. You're always going to have numbers. Maybe just have a graph without the numbers, just a basic picture. Not fully labeled, just a sketch, I guess. So then you're stuck making the graph or analyzing carefully what's going on. So we have two curves, y equals x and y is equal to 4. We want to find out which one is on top. Well, y equals root x is not a straight line, and y equals 4 is a straight line. And from this picture, the straight line is the thing that's on top. So top is equal to 4. The bottom is the curved part. So bottom is equal to the root of x, which is the same thing as x to the power 1/2. The bounds are a problem. We only have one bound. We have x is equal to 0, but need another bound. So I'm going to set y equal to y, which means root x is equal to 4. Then I need to get x all by itself, so I'm going to square both sides. Root x squared is equal to 4 squared. So x is equal to 16. That's my second bound. So my area expression is the integral from the lower bound, which is 1, to the upper bound, which is 16, of the top curve minus the bottom curve. So the top curve is 4, and the bottom curve is the root of x, which is x to the 1/2. And that might be the whole question. The whole question might be what expression represents the area. I'm going to roll from 1 to 16, or 4 minus root x. But I'm going to keep going, because it doesn't say just the expression. I'm going to take the antiderivative of each piece. The antiderivative of 4 is 4x. The antiderivative of x is the 1/2. We use the anti-power rule. Power increases by 1. 1/2 plus 1 is 3 over 2. And we have to divide by that new power, which is the same as multiplying by the reciprocal, 2/3. And then this can be evaluated from 1 to 16. So we plug in the top number, 4 times 16, 64, minus, plug in the top number in the second piece, 16 to the 3 over 2. I'll simplify that in a separate step, and then plug in the bottom bound, 4 times 1, minus 2/3, times 1 to the 3 over 2. Okay, so 64 minus power, so 16 to the 3rd over 2 power. So I'll use the power in the bottom first. The 1/2 power means square root. Square root of 16 is 4. We have 4 to the power of 3, which is 64. So 2/3 of 64. And for the second piece, I have 4 minus 2/3 times 1. We have 1 of 64 minus 2/3 of 64, which is 1/3 of 64. And then we have minus, and make common denominators here, minus 12 over 3, plus 2 over 3, negative, negative, plus, and then add all the tops together. So 64, let's see, so 54 over 3. Which is 18, I guess. Let me double check that. 18 times 3 is 10 plus 24. Yes, okay. No, 30 plus 24. What am I doing? 18 is 10 plus 8, so 30 plus 24, 54. Okay, yeah, that looks right. So 18 is the final answer that comes out. A nice number. What threw me off was I wasn't actually expecting this to be a nice number. I was expecting it to be a fraction. Okay, and then that's it for this topic of areas. See you in the next video.